Okay, we can start our seminar. Dear participants, our speaker now, Jules Lamers, with talk about Bethe ansatz inside the Calogero Sutherland models. Let us start.
All right, so thank you, and thanks to the organizers for having me speak here. I will talk about some recent and ongoing work joined with Didina Serban at IPHT near Paris, and also with Weyl, Ferrando, and Fedor Levkovich-Maslyuk, work in progress. And I encourage questions. So if you have any questions, please just interrupt me and ask. Right, so I'll talk about Calogero Sutherland models with spins and how you can do a Bethe ansatz inside of these models and what that teaches us. And as a motivation, let me go to two spin chains that I like a lot. So one is the Heisenberg spin chain, which I assume you have all seen before, and one is the Haldane-Shastry spin chain, which may not be familiar, or it may be. So for simplicity, let me just consider n spin 1/2 sites. So I consider here the SU2 model, but you could go to higher rank. And a lot of what I'm saying, what I will say will generalize to higher rank. But for the presentation, it's easier to just look at the SU2 case. So I want to compare the Heisenberg and Haldane-Shastry spin chains. And so the Heisenberg spin chain has this Hamiltonian, so we think of these spins as sitting on a circle like here. And for the Heisenberg model, the spins just interact by a permutation or maybe symmetrization or anti-symmetrization for nearest neighbors only. So only these neighboring spins talk to each other. We know all of this. It's an old model for magnetism. And of course, we love this model because it is an integrable model. So let me just, it's kind of useful to split this notion of integrability in three different notions. So one is that this model, in the analogy with what you expect from classical integrability, has a hierarchy of higher Hamiltonians. So these are known for the Heisenberg model, and this explains why the model is integrable in some sense. And related to having lots of symmetries, we can describe exactly, although not explicitly, the spectrum in terms of Bethe ansatz, and this is the parameterization of the eigenvectors, which works up to solving these Bethe ansatz equations. So it's exact, but it's not very explicit. You really need to solve numerically often equations to get the explicit eigenvectors. But this is very nice, and we can learn a lot from this. And of course, we all know that really the nice way to understand both of these properties is that the model is what I want to call quantum integrable, meaning in the algebraic sense of having an underlying quantum algebraic structure. So here, for the Heisenberg XXX spin chain, there is a Yangian underlying it. And if we construct the transfer matrix, then we get the higher Hamiltonians. So this is sometimes called the Bethe subalgebra of the Yangian, which gives all these higher Hamiltonians. Whereas if you do a kind of a highest weight construction, you get the whole spectrum. And this is the algebraic Bethe ansatz. So this quantum integrability is the algebraic underlying structure that allows us to understand both of these very nice properties for the Heisenberg model. Now, the Haldane-Shastry spin chain, on the other side, is quite different. So in this case, the Hamiltonian has this form. So again, spins interact via this exchange, the permutation of spins, but now they do so at long range. So any two spins interact in a pairwise way. And the spins interact more weakly if they're further apart. So there's a 1/sin² potential that makes sure that spins further apart interact less strongly. And this has a nice geometric meaning, this potential, this 1/sin², because if you think of this circle as being the unit circle in the complex plane, then it's just 1/r², where r is the chord distance between the two sides. So it's kind of nice. And this model was first found, well, it has applications in physics related to it being, you can think of it as a toy model or a lattice version of the fractional quantum Hall effect, in the sense that it has some sort of anyons appearing in the sense of exclusion statistics. And also you can think, and it has a wave function that looks a lot like certain wave functions that appear in the quantum Hall effect, but it's just a lattice model, so it's simpler. And another nice feature of this Haldane-Shastry spin chain is that you can think of this as kind of as close as you can get to SU2 level 1 Weyl-Witten theory on the lattice. So it has a lot of common structures with this conformal field theory. And you can think of it as kind of Westominowitten on the lattice. So it's a very nice model. And we can actually see this from its integrable structure. So in this case, the eigenvectors are known in closed form. So they're not Bethe equations. We can really write down the solutions to the Bethe equations if you wish. And we can write down the corresponding highest weight vectors explicitly. And another interesting feature is that this model does not have just a Yangian structure, but there is a Yangian and it really commutes with this Hamiltonian. So there's a lot of symmetry. We have a full Yangian worth of symmetries. This, of course, also means that the spectrum is highly degenerate because here we use the B operators to get new vectors with different energies. But here, if we would use B operators, we stay inside the same representation. So we have a model with a lot of symmetry, and it also has a family of commuting Hamiltonians. And I will explain how this works in due course. So the game that I want to play today is I want to kind of import this structure over here, where we have, rather than we have this Yangian and we want to construct a transfer matrix and then use an algebraic beta ansatz to construct its eigenvectors. So I want to use this structure from here to learn new things about this side here. And what this will give us is new Heisenberg-like symmetries. So not just the Hamiltonians here, but we will get extra Hamiltonians. And we will get a new eigenbasis for this model, which is nice because it looks more like what happens over here. And it has some nice consequences. So that's really what I would like to explain today. And in a little bit more, so let me, before I go to the outline of the talk, let me tell you kind of the reason why these models behave so differently. So for the Heisenberg XXX model, you can think of it as a natural inhomogeneous generalization where you attach a parameter to each particle. You can sort of think of it as a position, although the positions are fixed, they don't really move. And then if you make all these parameters the same, so you take the homogeneous limits, then you get back this XXX Heisenberg spin chain. And this inhomogeneous model really has exactly the same structure at the level, at this vague level that I'm talking here. And I'll review the inhomogeneous model in a moment because we will need it to learn to do this story here. Now, Haldane-Shastry has a kind of a much richer structure, really, in some sense, sitting under it, at least mathematically speaking. It's an extremely nice story. So what happens, in short, is that here there is a spin-Calogero Sutherland model sitting under it. So rather than just having a spin chain, we think of particles with spins, like I drew here, on a circle, moving around and interacting in a pairwise way. And this model is already very special because it actually already has basically all these special properties of the Haldane-Shastry model. So it has known explicit higher Hamiltonians, it has a Yangian symmetry, and now we can actually understand this at the level of the spin-Calogero Sutherland model, very nicely related to the degenerate affine Hecke algebra. So I will review this, and this is a beautiful story. And from this algebraic structure here, we can construct explicit eigenvectors again, and we can get these higher Hamiltonians. And so this has a very, very nice algebraic structure. And then we can take some limit called the freezing limit to get the Haldane-Shastry spin chain. And I think last week you had a talk by Masha Matushko. So she will have also talked about freezing, but I will review it separately. So you might recognize some things from what she talked about. And indeed, the type of models that I'm talking about are quite similar. The case that I have here is certainly better understood at the moment. And it is mathematically kind of a bit cleaner or easier. So it will be nice to kind of compare this if you remember last week's talk. Right. So the plan for my talk is the following. First, I will briefly review the inhomogeneous Heisenberg XXX model because we will actually use this. Then I will very briefly review some of these things that I already mentioned for the Haldane-Shastry model, that it has high degeneracies, that it has explicit eigenvectors, and so on. And then I will talk about this underlying model, this spin-Calogero Sutherland model. I will review how this whole story here works there, and I will review how this freezing business works. And then I will explain, once we have all these preliminaries in place, it will not be so hard to kind of use what we learned here in the context here, and then finally in this spin chain. And in the end, I will compare it to some other long-range spin chains and their underlying quantum many-body system. So that's the plan for today. So I repeat, please do interrupt if you have any questions. All right. So let's start. I assume that it's probably familiar to everybody, but it's better to make sure that we're all on the same page. So let me start from the inhomogeneous Heisenberg XXX model. So we start from the rational R matrix. I will draw it as a crossing as usual. It is just a linear combination of the identity and the permutation, normalized here in some way that the unitarity has coefficient 1 on the right-hand side. So R inverse is just the R of minus U. And it obeys, of course, the Yang-Baxter equation and this unitarity relation that I just mentioned. Then from the R matrix, as usual, we construct this, we take co-products in the physical space. So we get this L operator where we can put different parameters Z on each of the physical spaces. So these are the inhomogeneities. And this operator, because R obeys the Yang-Baxter, obeys this monodromy matrix, the RLL or RTT relations. Then we can take the trace in the auxiliary space. So graphically, that's what I indicate here by these little hooks there. And then we get the transfer matrix, which in this case is just A plus D. And we know, of course, that because of the RLL relations and generic invertibility of the R matrix here, this transfer matrix is a one-parameter family of commuting operators, which is sometimes called the Bethe subalgebra. If you introduce maybe a little twist, it's maximal, and it's a maximal Abelian subalgebra of the Yangian. So this is very nice, abstractly, and here in the representation. Now let me talk a bit more about this Bethe subalgebra, or the transfer matrix. So the transfer matrix produces commuting charges, but how do we get them in the general inhomogeneous case? So there are two things that one can do. So the first thing, which I think is most natural if you're used to normal spin chains, is you expand the transfer matrix at the simple point. So what we do is we take this U to be equal to any of these inhomogeneities there. That's a good point, because then one of these R matrices here simplifies a lot. So pictorially, what happens is that let's take U to be Zj, where that's the J parameter here. Then this R matrix, it just opens up and becomes an identity. And so the operator that you get looks like a series of R matrices, periodic boundary conditions, and then it kind of comes back to where it was. Here's the product in terms of R matrices, written explicitly. And now for each choice of J, we get such an operator. I'll call it Gj. And this is a family of commuting operators. And they have the property that if you multiply them all together, then you get the identity. Graphically, this is kind of clear. If you draw this picture with this opening kind of shifted everywhere, and you put lots of them on top of each other, then you will see that you just have something that is just the identity if you use this unitarity relation in the Yang-Baxter equation. Now, to connect it to things that may be more familiar if you have never seen this explicitly, if you take all these parameters to be the same, so let's say 1, then all these openings, all these crossings here open up. So what you just get is that this goes here, this goes here, this goes around in here, this goes here, and so on. So you just get a cyclic shift to the right. So this is the translation operator. And in this case, this relation becomes the relation that the nth power of the translation operator is the identity. But for general inhomogeneities, we have n different kind of deformations of this thing. We can't really interpret them as translation operators, but they're nice commuting Hamiltonians. And if you know the Godin model, then you know that you can do some sort of expansion of this, some sort of special semi-classical limit in which these become the Godin Hamiltonians. But we can go beyond. So for normal spin chains, we don't just have a translation operator, but we also have a Hamiltonian. And we do this by taking the logarithmic derivative transfer matrix. So with some computation, you can really compute this logarithmic derivative of the transfer matrix, and the result looks as follows. We will not really need it, but I think it's kind of a nice formula that I hadn't seen in literature. I'm sure that experts know this, but I think it's kind of cool. You can really explicitly compute these logarithmic derivatives at the same special point. So what happens is the following. You get a sum over, so again, we get n different Hamiltonians for each choice of inhomogeneity at which we take the logarithmic derivative. And then what we get is a sum of terms that have, well, I less than this fixed value, what happens here is that the fixed particle, it moves to I plus 1, then it interacts in the usual way, which I denote by a wiggly line here. So this is just the derivative of the R matrix at 0. So it's just the anti-symmetrizer, the usual interaction. And then it moves back again. And this transport here is done via R matrices. And then there's some little potential, which is quadratic. So this is what happens for all the sides to the left of this fixed particle. Then for all the sides to the right of this fixed particle, what happens is that the particle goes to the left and then periodically around to go again to the side k plus 1, so on the to the right of this particle, and then it moves back again with, again, the same potential. And then finally, there's some sort of weird term which you can compute explicitly, where the particle goes all the way around, then it interacts with itself in the future, then it goes all the way back, and then it interacts with itself in the past. And this wiggly line here, what it means is, well, we can write this interaction in terms of matrix units. So we just expand it in terms of matrix units in one side and the other side with some coefficients, which are 1 and -1 here. And then you just put this stuff here in the product and the second factor here in the product, or the other way around. So you can explicitly write this thing as well. And so you get a nice explicit expression for this Hamiltonian. By the way, if you would reverse the order of these two terms, you get the same quantity, but the expression looks a little bit different. And now instead of going to the left always, the particle goes to the right. So you get the left-right flips of all these expressions here. And it doesn't equal term by term to this expression, but it does equal if you take this sum here. Maybe for in a moment, let me already point out that we see that something special happens here if the two inhomogeneities are, well, if their difference equals plus or minus 1, because then the square of, we get a pole here at these kind of potentials. So we will see this value come up in a moment. Right. So this may look a little bit strange, but I think it's kind of nice that for this inhomogeneous model, you can really explicitly compute not only these GI, these sometimes called scattering operators, but also the kind of deformations of Hamiltonians. And you get lots of different Hamiltonians. And if we take the homogeneous, well, they all commute with each other. And if we send all the z's to the same values, then all these potentials disappear. And if you think about it, then everything just becomes nearest neighbor interaction. For instance, this guy here just goes there, and then like that. And this guy here goes there, and they interact like usual. So this is just, all of them become the same usual Heisenberg Hamiltonian. Now for later, for my purposes later, this evaluation at a special point, which is what we normally do to get the spin chain Hamiltonian, is not so convenient. So instead, what we can also do is we can expand the spin chain at a good, for instance, as a power series in U. So let me write it like that. And then we can compute these operator values coefficients. So the first two of them are not so interesting. But if we continue a little bit, then here we see, well, the quadratic Casimir. We find a sum of inhomogeneities. This is a scalar, not quite nice. But then if we continue, here we get some sort of sum of cyclic of 3 cycles permutations. And then we get a sum of z squared. And we get this extra thing here, which will be a bit more interesting later on. And of course, you can compute more and more coefficients like this. So these are also all commuting operators. And this is another way to present the Bethe subalgebra, some elements of the Bethe subalgebra. So the moral of the story is, we take this inhomogeneous transfer matrix, we get a 1-parameter family of commuting operators, which generates some abelian subalgebra. And here these and these and these and these are all elements of this commuting subalgebra. So this is useful to know about the inhomogeneous Heisenberg spin chain. Any questions at this point? Or is it all clear? Okay, so if no protests, then I will continue. So now let's go to the Bethe ansatz. So this is what I had before. I'm just repeating some stuff. So now in terms of representation theory, what happens here is that rather than just having a product of spin 1/2 sides or C2, we take a tensor product of evaluation representations, which I will denote by C2 with an extra parameter. So for each side, we put not only a spin, but also the parameter, these evaluation parameters. And then if we think of them as indeterminates, then we have this relation that the R check matrix, which differs from the R matrix from before by multiplying by the permutation. The R check matrix in the difference of inhomogeneities has the property that if you move it through the L operator, then it swaps these two inhomogeneities. So this is a nice property. It's sometimes called the exchange relation. And it says that if you have two inhomogeneous monodromy matrices, you can swap around inhomogeneities using the R-check matrix, more or less. So more precisely, if the inhomogeneities are generic, so that means that they do not differ by plus or minus 1, then this R-check matrix is invertible. So in that case, this operator here is really conjugate to this one here. So they have completely the same spectrum, and we can kind of think of them as really the same, describing the same model. So in this case, we have generic inhomogeneities, and what happens is that the big Yangian representation on the big space here is irreducible. So we can get everybody from starting from one vector. So for instance, this up, 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 up pseudo vacuum. And in this case, as I already mentioned, the order of the sets is not really important because the irreducibles are isomorphic, so we can move around inhomogeneities by conjugating with R-checks. Now, in this case, we know, but let me just draw it here. The structure of the Hilbert space is the following. So here, each dot represents a basis vector. And here, the number of downspins, so the weight spaces are labeled like this. So here, there are no downspins. So this is the vector up, 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 up. Here, everybody is a downspin. So this is down, 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 down. And then, of course, we know that we have an SL2 irreducible here, and we have another we have a bunch of SL2 irreducibles. So here we see this standard decomposition. And the algebraic beta ansatz says that we can start from this pseudo vacuum. We can act on it with this B operator, which is the guy that you get from here. You insert a downspin here and extract an upspin here to get one extra downspin here. So this gets you from here to either this level, or if you act by B operators twice, you get to this level, and so on. This is not quite an eigenvector of the transfer matrix, but it is if those parameters here or here, depending on where you want to live, satisfy the beta ansatz equations. So from my point of view, here we have a highest weight vector. We act by a number of B operators. Then we get a general linear combination that spans this weight space. And then you solve beta ansatz equation to really select an eigenvector of the transfer matrix, like that. And for these generic inhomogeneities, it's known that the algebraic beta ansatz, so this construction here, is complete. You really get everybody, all of these vectors from this guy here by using this story. Now, for us, it will actually be important to also understand this other case, which of course is well known for experts. Namely, what happens if these inhomogeneities differ by plus or minus 1? So this is the case where we had poles in the previous explicit descriptions of the inhomogeneous Hamiltonians. So in this case, the R-check matrix becomes a projector. It becomes either the symmetrizer or the anti-symmetrizer of the normalization. And in this case, it means that the Yangian representation is reducible, but indecomposable. And the order of these z's, which differ by 1, so whether this is plus or minus 1, determines which is the invariant subspace in here. So now the picture is as follows. If we have two inhomogeneities differing by plus or minus 1, like here, then there are two cases. Either the R matrix becomes, in the plus case, it becomes a projector like this, and its image here is a nice invariant subspace. So it means we can still kind of do this whole construction here, and the only thing that happens is we do not ever land in here. So we can still start from up, 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 up. We can apply a B operator, we get something here. We apply two B operators, we get stuff here, and so on. So this is a nice invariant subspace. However, there are some, in this case, there's some part which is not invariant. And so it means that if you want to talk about completeness of beta ansatz, these vectors are not of the usual algebraic beta ansatz form. You cannot get them from this guy by acting with B operators. So you have to be clever to get this. However, if you manage to get in here, then you can apply B operators and you will land not only here actually, but you will land somewhere in all of this. And that's why it's indecomposable. So this part will, if you act on it with the Yangian, you will land not just in here, but really in all of this together. Whereas in here, if you act with the ABCD operators, you always stay in this yellow part. So this was the case where we had the plus. If instead we have the minus, then this R-check matrix becomes the anti-symmetrizer. We can look at its image. It's the smaller part here, the complement from what we looked at before. And now we have the nice feature that actually we can get this vector in here from stuff in here by applying the B operator at the average of those two inhomogeneities. So that's kind of nice. So now here we have an explicit vector, which is of beta ansatz form. And then we can use beta ansatz to get everybody in here. If we want to get everything else in here, then we can use the usual beta ansatz. So we act on here with the B operator, but we get a linear combination of all of them. So we have to explicitly kill this vector here. We have to take a quotient. So you get stuff in here, and it's of the usual beta ansatz form modulo things in here. So this is, of course, well known. This is called fusion procedure. So if you take two inhomogeneities differing by +1, then you can fuse two sides to a bigger side. So here, this looks like we kind of made, instead of having 4 spin 1/2 sides, we have a spin 1/2, then a spin 1, and then a spin 1/2 side. Whereas here we have just spin 1/2, spin 0, and spin 1/2. So I hope that this is familiar, but if not, here you have an idea of how it works. And this is what will be common.
Sorry, I have a question.
Yes, please.
Sorry,
Yes.
yeah. So in the first situation, what is the general procedure to build highest vector for this second part?
Yeah, right.
There is some special.
So luckily for what I will tell you, we won't need this. But so what I know is, but it's not very nice. What you do is you just take some general vector in here, and then you kind of have to kill everything that's in here, and then you land here. So you can take a quotient, but I don't know of a neat explanation, like an explicit description of this vector here. So maybe other experts know how to do this, but I don't know. I mean, if you do it case by case for low length, then you can just construct it by kind of explicitly constructing things in here and then looking at what its orthogonal complement is.
But it should be also some kind of Bethe vector. I mean, you have some own vacuum that you can act by something or not, or it's I mean, this separate component, how it works.
So one thing to notice is that in this case, so I drew this arrow, but only this way. So what it means is you can never get here by starting from here. So you cannot act with the B operator on this here to get here. This is impossible. However, if you take this, if you are able to find this vector, then it's not killed by the C operator. The C operator will send this to this here. So it's not Yangian highest weight.
But the second case, you have something which can be killed by
exactly. So this is kind of nice. So in this case, I can actually explicitly describe it by acting by the B operator at the average inhomogeneity. And moreover, it is Yangian highest weight because I will not go back. So if I act on it by a C operator, I will actually kill it. So this case is very good for beta ansatz. This case is not so good for beta ansatz. So that's why I put this cross here. And if anybody knows how to explicitly construct this in general, then it would be nice. I mean, like an explicit construction of this vector, but I have never, I don't know. Right, so these cases are a little bit different. But luckily for us, we will only need these nice parts which work, where everything works very well, these invariant subspaces. Okay, so this was a review of some things about the Heisenberg spin chain, really. The normal homogeneous case falls under this class here because all the homogeneous fields being equal is generic. But for what we will see later, actually, we will both get this and we will get this. So it's important to understand both cases. All right, so now let's switch from Heisenberg to Haldane-Shastry. Here's just one slide to kind of show you the state of the art, more or less, for Haldane-Shastry. So remember, this is the Hamiltonian. I changed a little bit the normalization, but it's not important. Then its spectrum are labeled by something that we call motifs. They're simple patterns defined as follows. You just take, let's say, an M tuple of integers. I should have written that this is integers from 1 to n minus 1, with the rule that the integers cannot be equal and they cannot be adjacent. So for instance, if you have n is 4, like in this picture, then I can choose either nothing, empty, for m is 0. I can choose 1 or 2 or 3 for m is 1, and I can choose 1, 3 because they differ by these two, which is this rule here. But I cannot choose 1, 2 or 2, 3 or 1, 2, 3. So these are the motifs for length 4. So it's a very simple combinatorial pattern. Then for the Haldane-Shastry, for each such motif, note that, by the way, naturally this m is bounded to be at most the length over 2 because of this rule. So for each of these patterns that you choose, the momentum is very simple. So you just add all these numbers and you multiply by 2 pi over n, and that's the momenta. In other words, what is actually true is that you can think of these motifs up to this 2 pi over n as a quasi-momentum. That is to say, if you think about this in terms of Bethe ansatz language, then this is the solution of the Bethe equation. You first choose some integers, and then the quasi-momenta are just these integers up to normalization. So in Bethe ansatz language, there are only one strings, no bound states. Everything is purely scattering, and they completely do not interact, except through this rule, this kind of statistics rule that says that you cannot choose equal or adjacent momenta. So it's very, very simple. And then the energy is even more remarkable. It's literally the sum of one particle energies. So again, no bound state anything, no scattering corrections, really strictly additive. And the dispersion relation is very simple. It's just a quadratic formula. So here you have mu, one of these, and for each of these entries, you take that entry times n minus the entry. And with this normalization, divide by a half, and that's the energy. So this is also very, very special. It means that all the eigenvalues are non-negative half integers. So this is extremely bizarre. If you build this Hamiltonian in, let's say, Mathematica, you look at it, you see a Hamiltonian with some, lots of complex entries, and then you ask for all the eigenvectors, and you will see that they are just half integers. So in this case, for length 4, for instance, you get 0, you get 2/3, you get 2, and you get 3 occurring. And the fact that these values occur is because of this rule. Oh, sorry, and this one is just the sum of this and this here. So it's really completely strictly additive. It's extremely simple spectrum. It would be very, very hard to kind of just guess a Hamiltonian that has such a nice form while looking kind of a bit complicated like this one. So it's really very, very remarkable. Very different from the Heisenberg spin chain. Now, moreover, we can write down explicitly which vector has this energy and this momentum. Namely, what you do is, so here I just have, this is the wave function of the vector for a given motif, mu. And what you do is you take a van der Monde squared in m variables, and you take a Jack polynomial in m variables with some partition that is determined by the motif. I can tell you how it works if you want. And this is just a Jack polynomial at a very special value of the coupling, 1/2. So these are called zonal spherical polynomials. So this is the wave function. And what you need to do is you need to set, oh, sorry, I forgot to write this. You need to set the variables to complex roots of unity. Maybe I should write, sorry, is that j is e to the 2 pi I j over n. In other words, if we think of this as being the unit circle in the complex plane, then the nth particle, the nth downspin, so these zm's are just the positions of the downspins. So this is the second nth root of unity, the third one, the fourth one, and whatever. So those are the blue values that occur in here. So very simple. So these Jack polynomials are very well studied. Van der Monde squared is even easier. You just plug in this special value of the coupling, or the parameter of the Jack polynomial. You just plug in these special values, these roots of unity values for the variables, and then you get the wave function. And you just build a vector as usual with the downspins at those locations. So very, very explicit, very nice. And in particular, for instance, if you want to know if you have length is even, then there is a motif, which is of the form 1, 2, 3, 5, n minus 1. So this one is sitting at the equator. It is maximally simple. So in this case, the Jack polynomial is just 1. So it turns out that in this case, this nu of mu is just 1 to the m. So very simple partition, which means that this guy here is just the product of all the variables, zi1 dot zim. So this wave function here is basically just a van der Monde square. And this is the wave function that I mentioned before that's similar to the wave function Laughlin state from the fractional quantum Hall effect for filling fraction 1/2. So it's very, very simple and nice. And in fact, this feature is how Haldane and Shastry independently found this model. They were looking for a model that had this as a ground state wave function, and then they found that this Hamiltonian does the job. Now, moreover, I just told you what these vectors are, and in terms of my pictures, they correspond for each motif to these highest weight vectors. And they're not just normal highest weight vectors, but they're Yangian highest weight vectors. You see that here is something which, if compared to the Heisenberg model, we wanted to separately construct all of these vectors because they are only on top of kind of on SL2 irreducibles. But in this case, we have more symmetry, and this one actually is not just on top of this SL2 irreducible, but on top of a bigger Yangian irreducible. And if you increase the length, then of course these representations will get bigger and bigger and bigger. So they're bigger, much more degenerate than in the Heisenberg case. And this is because of the Yangian action. So I don't really want to spend too much time, but we know explicitly the Drinfeld polynomial, basically it's like a product with factors differing by 1. So this is sometimes called a string in terms of Drinfeld polynomial. So it has a very long string, except that we drop factors determined by the motif. And you drop 2 adjacent factors whenever you have an entry of the motif. And this is a sort of a way to understand that you're not allowed to have neighboring numbers here. And the Yangian act by the usual SL2, supplemented in the Drinfeld first presentation, this J presentation, by some kind of split commutators with coefficients that are cotangents. I don't really want to go to think about this too much, but it's explicit. So these operators allow you to get this guy here, for instance. So this is very nice and very explicit. This is a complete explicit solution to the Bethe equations, if you want to think of it like that. And then we have a wave function, which is not a beta wave function, but instead some sort of other type of nice wave function. And we have extended extra symmetries, which make higher degenerate spectra. So that's how the Haldane-Shastry model works. Now, this was most of this was found kind of originally by kind of just looking at examples for small n and by kind of guessing and trying and so on. But later it was understood where this comes from. And here's the cartoon. I will develop this in more detail later, but let's first think about this. So here we have this Haldane-Shastry spin chain. And I already said that the wave functions here, if you think about the certain number of downspins, then you get this van der Monde squared times this special Jack polynomial. That is actually a wave function of the trigonometric Calogero-Sutherland model, whose number of particles is precisely the same as the number of downspins here. And it has this special value of the coupling alpha is 1/2. So somehow the spectrum of Haldane-Shastry comes from a relation to a spinless Calogero-Sutherland model at a special value of the coupling. Now, the reason for this is the following. There's some underlying algebra called the degenerate affine Hecke algebra, which is known to be related to these trigonometric Calogero models. But you can also relate, and I will explain how this works in a moment, get from it a trigonometric Calogero-Sutherland model with spins. So now we don't just have particles moving on a circle interacting in pairs, but they also have spins. And this model is very nice because it already has Yangian symmetry, as I mentioned before. And then, as I also mentioned before, we can take this special limit called freezing. And this here, we have commuting Hamiltonians and a Yangian symmetry. And from it, we get commuting Hamiltonians and a Yangian symmetry for this Haldane-Shastry spin chain. And moreover, this whole framework allows us to also understand this connection here. I will not have time to really talk about this, but really the integrable structure of Haldane-Shastry comes from thinking of it as sitting inside this bigger picture. And all the nice properties, the Hamiltonians and the Yangian, they really come from the fact. And also the explicit wave, the eigenvectors come from the fact that this model here has this extremely nice algebraic structure already. So my next part of the talk will be to explain how it works here. All right, so what actually does this spin-Calogero-Sutherland model look? So we think of these particles sitting on the unit circle, let's say, moving around. They have spins and they interact in some way. And this model is integrable. So we have lots of commuting Hamiltonians. So of course we have a momentum operator, which is just the sum of all the individual momentum. It's kind of a derivative in all the coordinates. And then we also have an Hamiltonian. Here is just the usual kinetic energy, the Laplacian minus 1/2 times the Laplacian. And then we have this interaction pair where we have a potential 1/sin², just like for Haldane-Shastry. And then in top, we have this coupling constant. So remember, so in the scalar case, this permutation is a spin permutation. In the scalar case, it would be absent. So in the scalar case, you would have beta minus +1. And this, you think of this as the coupling constant. So it's kind of instead of what usually you might write as g². But it turns out to be useful to not write g², but with this little shift here. And the minus and the plus I will get to in a moment. So what you see here is that this part here is just a scalar potential, but then here there's also some spin interactions with this 1/sin², which is the 1 over the chord distance, just like for Haldane and Shastry. Okay, so, and there are actually many, many more higher Hamiltonians. So where did they come from? So what we will do, and this is also going to be the connection to the story about the inhomogeneous spin chain, is we're going to think of these evaluation representations from the inhomogeneous spin chain as instead being the space of polynomials with coefficients that are complex two-dimensional vectors. So each particle has a spin and a coordinate, and I want to think of this model as being polynomial in these coordinates. That's good enough because we're trigonometric here. These z's, by the way, they will be related to the x's in the top in this way. So here I will work with multiplicative variables, z, whereas here I use this additive variables. Okay, so for each of the particles, we have this evaluation representation, and we think of it as polynomials, vector value polynomials. And then for n particles, we take the n-fold tensor product. So we can think of this space as being the usual spin chain Hilbert space times the space of all the polynomials in n variables. Now this space is kind of a bit too big, but it's nice for the following reason, that it has a representation of this algebra that I mentioned before, the degenerate affine Hecke algebra. So what this is, of course, in here, we have polynomials and variables. So we have a natural action of the symmetric group, which just acts by swapping coordinates. I will sometimes call these z's coordinates. So you just permute in here, and that, of course, gives a representation of the symmetric group. Now, there's something else that you can do, and that is, there's these operators called Dunkel operators. Here is the explicit form, but I don't really... So the important thing is that each Dunkel operator is like a derivative, now in multiplicative notation, but it's just like this part here, basically, with this 1 over beta, where beta is a parameter. So Dunkel operator is defined for a choice of a coupling constant beta. So here we see just a kind of like a kinetic energy, connection in some sense, with kind of corrections or extra stuff that permutes coordinates with some explicit rational coefficients, whose form is not so important. But this whole expression is precisely so that it obeys the following relations. These Dunkel operators, they commute with each other. So they form an abelian subalgebra of the degenerate affine Hecke algebra. And then the relations with respect to these permutations of the z's are the following. If you move a Dunkel through a permutation with kind of the same indices, then you move the index, you change the index of the Dunkel, and you get an additive constant. So that's what it is. And from these relations, you can show that the center of the degenerate affine Hecke algebra are just symmetric polynomials in Dunkel operators. So if you take the sum of all Dunkels or the sum of Dunkel squareds or things like this, then you get operators that commute not only with Dunkels, of course, but also with all the permutations. And this will be very important for us because this is where the Hamiltonians come from. But before we go there, let me tell you one more thing about these Dunkel operators. Namely, they commute with each other, and they're actually a maximal abelian subalgebra of the degenerate affine Hecke algebra. So they have, on this representation on polynomials, common eigenvectors, the Dunkel operators, which are called non-symmetric Jack polynomials. And they have very simple known eigenvalues, which are basically, so for each, you take well, not really a partition, but an n-tuple of integers. And let's say we sort them for simplicity. Then the eigenvalue is just this 1 over beta times the integer with a little correction. And there are some things change a little bit if this thing is not sorted decreasingly. But we know how it works. So the story is that we have this nice maximal abelian subalgebra, and in this representation, we know there are common eigenfunctions, which are non-symmetric Jack polynomials. And they depend on this parameter beta here. All right. So this space is good because it has this representation, but it's not really, for physics, it's not so good. So we want to look at the subspace of it, which we call the physical subspace. And we can do this either for bosons or for fermions. So what we do is, well, if you think about this degenerate algebra, it's a bit boring because really it only acts on this vector here. It does not do anything to the spins, which is a bit kind of not so nice. So we want to somehow kind of couple these two. So physically, what you want to do is you want to say that you want to look at vectors or particles which are either totally symmetric for bosons or anti-symmetric under permuting simultaneously the z's and the spins, right? So if we have two particles, then they each have a spin in a coordinate z. And if we swap them completely, then we swap the two particles, and we should either get plus or minus the same for bosons and for fermions. So there's a bosonic subspace and a fermionic subspace. And now the nice thing is that this condition here, well, it's built from permutations. So certainly it commutes with the center of the degenerate affine Hecke algebra. So what I can do is I take this in this center. Let's look at the sum of the Dunkel operators. Then if you take the sum of all of these, all this stuff here cancels. So you just get the sum of all of this. And if you switch to additive coordinates like here, then you recover this up to a factor. So this is the first commuting Hamiltonian. Then with a bit more work, you can show that if you take the sum of the squares of Dunkel operators, then you get these Hamiltonians, where this plus and minus sign comes from changing the permutation of the coordinates to the permutation of the spin with the sign according to this invariance condition. And then you can also look at the sum of cubes of Dunkel operators or other combinations, and they all commute with each other, and they commute with anything from the degenerate affine Hecke algebra. And the nice thing is that they preserve this space because of it. So we have a family of lots of commuting Hamiltonians on the bosonic or fermionic physical space here. But this physical subspace has another extremely nice property, namely it is a representation of the Yangian. And the Yangian is defined as follows. So we define this monodromy matrix, the L operator. And what we do is we basically take an inhomogeneous monodromy matrix like before, where we replace the inhomogeneities, Z, J, from before, by minus or plus, depending on whether we have bosons or fermions, the Dunkel operators. So this sounds very weird, but if you think about it, then you can make sense of this thing here as an operator on this subspace in here. And the fact that it preserves this subspace is non-trivial, and it really uses all these relations in here. And moreover, of course, it commutes with the center of the Dunkel operator, the degenerate affine Hecke algebra, because this commutes with everything. So it also commutes with this here. So in physical language, the paper by Bernard, Godin, Haldane, and Pasquier, who found this expression, they call this quantized inhomogeneities, where by quantized, they just mean that they're operator-valued inhomogeneities. So here we have an L operator whose inhomogeneities act on polynomials. And this is a representation of the Yangian, because all the Dunkel operators commute, so they still obey the RLL relations. And if you take its quantum determinant, which gives the center of the Yangian, then you get back essentially the center of the degenerate affine Hecke algebra. So this thing here, you can actually recover, well, these operators here by taking a quantum determinant. So this is all nicely consistent. So what we now have is a big family of commuting operators together with a lot of symmetries of it, a Yangian worth of symmetries. Okay, so what does this give us? So let's think about what these bosonic or fermionic spaces look like. So it turns out that if you pick either the bosonic or the fermionic space, it's of course reducible for both the Yangian and these Hamiltonians, but it does so in a very nice way that we can explicitly write. So it becomes a sum over partitions of length at most n. So these n tuples now ordered, length at most n, and each of these subspaces in here, they have known momentum for the operators that I forgot to write, this total momentum operators, and here for the Hamiltonian. These eigenvalues, by the way, are just as in the scalar case for a scalar Calogero Sutherland, which means that in here we just replace these, we replace these permutations by, I don't know why it's doing this. We replace these permutations here by 1. So in that case, we have precisely the same eigenvalues. And of course, they come just from the eigenvalues of the Dunkel operators. And moreover, each of these summons in here is an irreducible representation for the Yangian. And so what it just means is we have a lot of the same eigenvalues. So there are lots of degeneracies because of the Yangian. And these irreducibles here, they have a very nice explicit description. So we can think of this as for each of these subspace. So we choose a partition of length n, at most n. And for each such partition, we get a subspace, and we can think of it as an effective inhomogeneous Heisenberg spin chain, where the inhomogeneities are specific now numbers, which are the eigenvalues of those Dunkel operators that I showed you before. So these are just the eigenvalues of the Dunkel operators on the non-symmetric check polynomial. So before, remember in general, here we have an L operator with minus or plus the Dunkel operators instead of inhomogeneities. But now if I fix a partition, then I can replace these operators by their eigenvalues. So I just get a model with fixed inhomogeneities, numerical values if you fix beta and lambda. And this just looks like the L operator of an inhomogeneous XXX model, which we studied before. So the story is if the parts of the partition, so let's first look at this example. If this partition is strict, so none of the parts repeat, then what happens is that the corresponding inhomogeneities, which are these eigenvalues of Dunkel operators, they're generic. So because of this expression here, with this kind of explicit shifts in here, you see that for generic lambda and beta, let's say positive, these eigenvalues, these inhomogeneities here are generic. So it means that we have one huge irreducible. So it looks just like a spin chain of length n. And the isomorphism is the following. In here, you take the vector up, 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 and it is sent to either the symmetric or van der Monde times symmetric Jack polynomial. So this comes, of course, from this non-symmetric Jack polynomial by symmetrization or anti-symmetrization. So it's very nice. So in this space here, we can explicitly describe the highest weight vector, and in this way get an isomorphism with a spin chain of length n with generic inhomogeneities. So we know here that the beta ansatz is complete, and now we can use the algebraic beta ansatz. That will be the strategy. However, if these partitions have repeats, then what will happen is fusion. Because if you look at these eigenvalues, the inhomogeneities here, if a partition has repeats, then the only difference between the corresponding deltas is precisely this step of 1. So we're precisely in the not, so this difference of the deltas is precisely 1. And then depending on whether you have a minus or a plus sign here, you get fusion. Either like for bosons, you pick up this big invariant subspace, or for fermions, you pick up this small invariant subspace. And the nice thing is that, as I told you, in this case, you can just use the beta ansatz with the highest weight vector that is a bit like up, 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 but now for a spin chain with lower length. And or you can apply to up, 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 this B operator at the average of these inhomogeneities. And then we get an explicit Yangian highest weight vector in here, and we will use the beta ansatz. So that will be the strategy. So it's very nice, I think. So either we have a generic case, or we get some fusion, where for bosons, we always fuse into the symmetric, so a higher dimensional irreducibles, or for fermions, we fuse to smaller irreducibles. We essentially remove a side. And the invariant subspaces are the parts that occur in our big physical space. So this is a very elegant picture. And this was found, I should mention, by Takamura and Uglov in the late 90s. Okay, so I basically already said at this point, but let me just go a little bit more explicit on this. So now we put together everything. So now we have this big model where we have lots of kind of like inhomogeneous spin chains where fusion may or may not occur depending on whether the partition has repeats. And then we can construct first Heisenberg-like symmetries, just like I told you how to construct them for the inhomogeneous XXX model. So the first version, we got these kind of inhomogeneous analogs of the translation and Hamiltonians, but they don't preserve on the physical space here because in here we have a kind of a nice symmetric condition. And if we here instead, we set these spectral parameters to very explicit values. So that's not good. It kind of breaks the symmetry in here. So rather than acting with these, what you can do is you can do this expansion of the transfer matrix as a power series. Now I also introduced a little twist, which I call phi. Then, because it's nice for, well, I will see in a moment. So then these guys are still constants, but now the things that I computed before become more interesting. So let's for a moment think that phi is absent. So let's just ignore all the light gray stuff. Then here again, we get the quadratic Casimir. And now remember, we have the sum of z's. Now it becomes a sum of plus or minus the Dunkels. So this is the momentum operator. So that's nice, but it's not new. It's just one of the things of the spin-Calogero Sutherland model that we already knew. In here, we get a sum over 3 cycles, okay? Then we get the sum of Dunkels squared, which is just the Hamiltonian from before, which is nice. And then here we get something that is really kind of new. So it's very different from just being in the center of the degenerate affine Hecke algebra like that. And so this is beyond the quantum determinant. This is something that you would not get from the quantum determinant or from the center. And it's not the Yangian invariant. So, but it still commutes, of course, with all the other operators. So this is what I call a Heisenberg-like symmetry, because the construction is like for the Heisenberg model using a transfer matrix. And then we have something here that commutes with the momentum operator and the Hamiltonian and all the higher Hamiltonians. But this guy itself is not Yangian invariant, which is good because now we can start doing beta ansatz for it. Of course, this decomposition, it was a decomposition for the Yangian, so it's respected by the transfer matrix. So for each of these irreducibles, what happens is we can do an algebraic beta ansatz. So we can do the algebraic beta ansatz on one side or on the other side. So this guy here is what I mean. It's kind of the image. It's what I did here, or the vector that I would get there, and so on. So you can explicitly, now for each irreducible, you get an explicit highest weight vector, which we can describe. I haven't really done it, but you get it from non-symmetric Jack polynomials by some symmetrization or anti-symmetrization, and then you build a spin vector from it. And then that will become a highest weight vector, and you act on it by B operator, which has inhomogeneities replaced by the eigenvalues of Dunk operators for that partition. So this is basically we get an algebraic beta ansatz for each part in here. And this works well precisely because of this picture here. We either do it generically, where it works fine, or we do it in here, which is fine, or we do it in here, and we know how to get there from there. So we can always describe it in terms of a form of an algebraic beta ansatz starting from up, 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 up. Very good. And now here I included some twists. So if you take this diagonal twist, right? So I take my transfer matrix just to be phi A plus phi inverse D. So a diagonal twist. Then this part is not so interesting. But in here, we see that with the twist, even this is already different from the momentum operator or the Casimir operator, but it becomes some sort of non-trivial combination of both. And even this would break the Yangian symmetry, but it's a good extra Hamiltonian, Heisenberg-like symmetry, which is not Yangian invariant and for which we can use the beta ansatz to construct its eigenvectors. And since all these operators here commute with the center of the affine Hecke algebra, the degenerate affine Hecke algebra, so it commutes with the spin-Calogero momentum operator, the spin-Calogero Hamiltonian, and so on. This algebraic beta ansatz basis that we construct is also an eigenbasis for the spin-Calogero Sutherland model. So for spin-Calogero Sutherland, we could just get a new explicit description of all the eigenvectors, not just the highest weight vectors. And adding the twist here is nice because if we send the twist to infinity, then, well, if you take this operator, let's say we normalize it like this, then if we send phi to infinity, we just pick up the A operator. And in this case, the beta ansatz equations become very simple. We can solve them explicitly, and we get the Gelfand-Zeppelin basis, which was described by Takamura and Oglov. So from this point of view, by doing this internal beta ansatz, this algebraic beta ansatz construction inside each irreducible, we get the generalization of the Gelfand-Zeppelin basis in terms of eigenvectors for the spin-Calogero Sutherland model. So I think this is all quite elegant. Right, so I've talked a lot, but I haven't really gotten to the spin chain yet. I understand that time is always up, so I will conclude quite quickly. So now we continue to do what Masha told you last week. So what we do is we send this coupling to infinity. And very briefly, here's the spin-Calogero Sutherland Hamiltonian. Let's think of it in terms of this expansion in terms of beta. So there's a part beta squared. It's just a constant. So it's not very nice, but I mean, it's not a nice, interesting operator. Let's just minimize this. Then we look at the subleading part, which is this here. And here we recognize that this looks a lot like the Haldane-Shastry spin chain. But doing this is not quite good. So what we want is we want to simplify this as much as possible. And to that end, we send these variables z to those roots of unity that I mentioned before. Then these are classical equilibrium positions. This is minimized. And it turns out that this part here is a member of a family of commuting higher Hamiltonians, precisely at this value here. And at these points here. And if you take this operator at these values, you precisely get the Haldane-Shastry Hamiltonian up to maybe a shift. So this is where the Haldane-Shastry model comes from, this spin-Calogero Sutherland model. And we also had an L operator for the spin-Calogero Sutherland. So if we send beta to infinity in there, we can just do it immediately, and we get an L operator for Haldane-Shastry. That's where these Q's that I showed you in the start, where they come from. And this guy in here still commutes with all those higher Hamiltonians. And that's where Haldane-Shastry with its higher Hamiltonians and its Yangian symmetry come from. Now we can repeat the game from before. So for each motif, we know this Yangian highest weight vector for Haldane-Shastry. Well, I haven't told you how to derive it, but at least I mentioned it. So we construct the corresponding Yangian highest weight vector, and then we now use this as our highest weight vector for the beta ansatz. And then we can do a beta ansatz construction of the whole spectrum of the Haldane-Shastry spin chain, using the story from before where fusion may or may not happen. Okay, and of course, in this case, only certain partitions occur because it's a finite dimensional Hilbert space. So basically, everything that we did, if we understand how to do it for spin-Calogero Sutherland, then in principle, we understand how to do it for Haldane Shastry. Okay, so here's the summary. Maybe let me skip the very last part about long-range spin chains and quantum many-body systems. So what I've shown you is that there's this algebraic structure, which normally is understood to be related to trigonometric Calogero Sutherland, but you can also, it's also known to be related to the trigonometric spin Calogero Sutherland. By freezing, we get the Haldane Shastry model together with its commuting Hamiltonians, and not just its, which also arise from here, but also together with Yangian action and an abelian subalgebra, which gives these extra Hamiltonians. And we could do a Bethe ansatz type construction using this structure here to get a very nice story that for each partition, essentially, depending on whether we have bosons and fermions, we get some effective inhomogeneous spin chain, which may or may not have fusion. Algebraic Bethe ansatz works very nicely, so we always get eigenvectors of this type in here. And this is a new eigenbasis for spin-Calogero Sutherland and for Haldane Shastry by freezing. And finally, let me mention that all of this generalizes to the Q case and to higher rank, I believe. I haven't worked out the details, but everything is in the right way to make this work without any problem. And one way why we liked to do this with Gwenel and Didina and Bethe is because now we have an algebraic Bethe ansatz type of construction, and we can also think about separation of variables for long-range models. So for trigonometric spin-Calogero Sutherland or for Haldane Shastry. And this is interesting, for instance, for them, they're quite interested in integrability and ADS-CFT correspondence, and there it would be useful to understand very well how separation of variables works for long-range models, because they appear naturally in ADS-CFT too. So with that, let me conclude. So thank you for your attention, and I'm happy to have questions, if any.
Questions.
Okay, very nice. Any questions? Comments?
I have questions.
Okay.
Mm-hmm.
Okay.
In your case, you can write some kind of Bethe ansatz equations, Bethe equations, and your left-hand side you have ratio of two different polynomials, as usual. But it turns out that solutions also quite nice. Because I know this deformation, and it also has, Haldane deformation, and it also has good spectrum, integer spectrum. So it means that this square combination of energy which give you, in this case, it's some separate functions in integer spectrum. So it means that solutions of this equation should be also integer or almost integer.
I haven't looked at this.
Did you not?
I've not looked at this. I don't think it is necessarily true that the Bethe roots themselves are very simple. I suspect that they're complicated. I think it's only true that if you put them in the energy and the momentum function with the particular shifts and so on that you like, that the result conspires to be very nice again.
I understand what you mean. Okay, so it's nice. Okay, it's good point. And one more question, if you don't mind. So in situation with Haldane Shastry, have you this situation with projection or not, with fusion or not? I don't understand. What did you mean?
Right. So for Haldane Shastry, so you see what happens.
Yeah, I understand. I understand the story with motifs, but I don't understand.
Right, but you see what for Haldane Shastry, we send beta to infinity. So we sort of remove this part here. So it looks like you would always get fusion. So it's a little bit, it's not completely trivial to actually work out the details here. There's some work to be done. So what happens for Haldane Shastry is, yes, you do get fusion.
Yeah,
it happens.
And this stories motifs always give you, yeah?
Right. So let me go back to this slide about So here you see the graph of polynomials, and you see that in general you have irreducibles, but they may have some fusion happening in there. If you look at dimensions that follow from this formula here, you will see that it would happen.
But as you told us, there is two types of fusions, plus a sympathizer with an anti-sympathizer. Is it true that in this case we have always only one fusions, and we can use this basis as all highest vectors and then produce all vectors in this system, or we need something more?
That's a good question. So the answer certainly is that's something I should have mentioned. So if you freeze, you can start from either the bosonic or the fermionic spin-Calogero Sutherland, and it turns out that both give the same Haldane-Shastry model, which is not so surprising, I guess. If you see the formula here, you just see that the difference between bosons and fermions is this sign here. So, you know, you get the Haldane-Shastry Hamiltonian up to some constant, which depends on the choice. So indeed, I have to think a bit better about the fusion case. So I'm sure that it works out nicely, but maybe this actually suggests that for Haldane-Shastry, in fact, in the end, the fusion doesn't happen. I have to think about the examples.
Okay.
So, right, so this is an explicit part of this, that is why there are still some X's in the title of the archive code. So this is the last part that we still have to think a bit about. So thanks for that question.
Okay, and other comments, questions, and so on. Okay, the next seminar will be devoted to considering of the higher Nienhuis brackets, the talk of the Professor Tim Testa. Okay, so we can finish now.